Like,
It's not a master. Yeah, definitely not.
just a seminar, right? Yeah, I was just confused. Sorry.
You can do that, but you don't necessarily have to present a master to present here.
Just research at the
Research,
seminar.
if you have an object in your research that can fill out like half an hour or so, you should do it.
That's good to know.
Yeah.
I'm not at that
They
point.
said, but yeah, okay.
I'm not at that point, but because I have my master's.
Alright, because there is a free spot next week, so.
I already signed up for my master's.
I'm going to introduce you.
What?
I'm going to introduce you. Here.
Yes.
Okay. Hello everyone, I'm really happy to introduce Nuo Chen, a great scientist and a great lab mate. So Nuo Chen started here at Grad School in spring 2020, right before the pandemic actually. And before that, she completed her bachelor degree at Nanjing University of Information Science and Technology. And she also spent 1 year at Shanghai Typhoon Institute, where she did research on characteristics of hurricane Vendavi layer. And she's now working on Adjoint Sensitivity that she will be talking about this today. So yeah, this is, take it over, you know.
Okay, so I'm going to talk about adjoint sensitivity, potential vorticity, and to geostrophic imbalance. And I noticed Michael gave this talk a year and a half ago about adjoint sensitivity on TV. So this work is supported by St. Bill Smith's scholarship. And I want to acknowledge the discussion with John, with Michael, and with Brad Hoover. So we want to dive right into it. The first part is going to be what is adjoint sensitivity, and I want to try to make sure everyone understands that before I go to sensitivity to PV and to imbalance. We define the sensitivity as the first order derivative of the response function R to the state vector X. The response function can be any forecast perspective, such as sea level pressure and precipitation at final time, and it can be written in the form or as a function of your forecast state vector. And note that the change in response function is the product of sensitivity and perturbation. It's just first order derivative. We have in numerical model, we have forward model. Of course, everyone runs model forward, no one runs it backwards. When we put in the initial condition and they run forward, we have final time output, and the response function is a function of the final time output. We can then linearize the model along the forward trajectory provided by nonlinear model and derive the tangent linear model, which it takes in initial condition of the perturbation and gives out the final time perturbation. The adjoint model is the transpose of the tangent linear model, and it takes in the final time sensitivity here, and then integrate it backwards to give you sensitivity of the response function to state vector at each time step. So these are all very abstract, and I want to put it in a case study. And I'm going to present the November wind storm of 1998. It's a bomb cyclone and deepened from 996 to 967, from November 10th 0Z to 11th 0Z, from here, Colorado region, to the Midwest. And it had sustained winds over 40 knots over Wisconsin and Minnesota. It's not gust, it's sustained wind. So for the forward run, we use the work model, and the time integration is from 9th of 18Z of November to 10th of 18Z. And the storm deepened from, in the model, deepened from 995 to 961. The adjoint is carried out by work plus, and we define the response function as the column dry air in this matched region encountered by 980 hectopascal. So this is to say, if we put in any perturbation that has the same sign as the sensitivity, it will lead the storm to deepen at final time. Any questions so far? Okay. So Here I'm just plotting out the 500 sensitivity weights in arrows and sensitivity to temperature shaded. So warm, red is warm, blue is cold temperature sensitivity. And you can see the majority of it is follow the 500 trough and just follow around to the final time. Looking at just one specific time at F12, you have cyclonic winds or sensitivity to winds going cyclonically around the trough, and cold air behind the surface front, and warm air sensitivity ahead of it. So that all leads to the storm to deepen. If we put in perturbation that has the same sign as it, as desensitivity, that will lead to the storm to deepen 12 hours later. And here it shows the water vapor sensitivity. You can see it just emerges from the Gulf and goes along the storm or the surface front, goes up toward north. And looking at it at one time, you see the main feature is around the surface front, and mostly with the cold front precipitation and warm front precipitation. And that is because the adjoint model highly dependent on the nonlinear forward model trajectory. And it's because it's nonlinear, and the water vapor is nonlinear, it's kind of had this switch on and off based on where you have your condition in the nonlinear forward trajectory. So how do we know these areas are actually sensitive, or it's just giving us some noise? We can prescribe a certain amount of energy that leads to the changing response function. And this energy here, we want to minimize it, is defined by the addition of kinetic energy and internal energy. And these, we want to put it into constraint, saying that the changing response function is a product of the perturbation we want to calculate or want to minimize. As product of it and the sensitivity. So we use the Lagrangian multiplier, sorry, this should be a minus sign here. And we find if we put the perturbation, initial perturbation, proportional to the sensitivity, that would give us the minimum energy that leads to a maximum change in the response function at final time.
So what's W in that case?
So W is the weighting function, so it will be 1 for U, 1 for V, and CP over P naught. It's a kind of diagonal matrix. So here's showing what it looks like for the initial perturbation, and contour is showing the sensitivity to, not sensitivity, but wind perturbation, and shading is the temperature perturbation. This is the perturbation what we're putting at the initial time. And it leads to a drop in final time sea level pressure. So this is perturbed realm minus control realm. If we put it, you remember the perturbation here, at F0, it gave us this drop in, well, it says 10 hectopascal drop, but it's actually 3 hectopascal drop in the minimum sea level pressure. And the dipole you'll see is because we have the shift in the position of the sea level pressure center. So this all says the optimal perturbation or sensitivity is valid, and it can indeed lead to the storm to intensify at the final time. Everyone okay so far? Yes?
I guess I could understand it. So like, how do you know where to perturb the values? Like, how's that chosen?
That's so here we perturb it proportional to the sensitivity.
And you do it for all of the values in the whole modeling domain, or is it?
Yeah, it's only putting the perturbation at the initial time, so we only need to take the proportional to the initial time sensitivity.
Okay.
And it's for I only perturb winds and temperature, but you can also perturb other variables like water vapor. Yes.
How sensitive is your perturbation to the desired response function box, which shows us the minor Pascal contour, right?
Yeah, it's more experience based. I think if it's larger, I'm not sure, sorry. It's a good question. I haven't tested different response function area. Okay, so to conclude the first part, we know the adjoint method is an efficient way to give sensitivity instead of running ensembles and trying to figure out which area is more sensitive. We can also perturb the initial condition proportionally to the adjoint sensitivity, and that leads us to the expected change of response function. So the second part is going to be about sensitivity to PV. And I want to leave you with this very ugly plot. Remember, we put in response function of tricolumn here at about this region at final time, so F24. Let it integrate backwards for 1 hour. It gives us this gravity wave. Give it another hour, gravity wave expands, it bounces back. So that's definitely unphysical, because in real world, we don't have a model domain, and it will just go out. Give it another 6 hours, it looks like this, and it's a mess. You can see some maybe physical feature here at this location of Missouri, but in general, we don't want to interpret this. And it's not just in the dry column air sensitivity field, it also shows up in the wind sensitivity field. So this is 300, and you can see in general a outgoing divergent wind sensitivity, and here in the center of it is some cyclonic wind sensitivity, which may be reasonable. But the divergent, I can't say it's reasonable, and yeah.
So how is that different from what you showed a moment ago with that?
It's like the fine and filtered result.
The previous one was the filtered result?
Yeah.
Got it.
I can show you something like this and say it's valid and hope you understand that. So we see this question at the very beginning of numerical development of numerical weather model, and Richardson kind of fails to do that because he finds there's some gravity wave and instability in his baroclinic model. And Charney, in his paper in 1955, suppressed the spurious inertial gravity waves oscillation and forward model by using a balanced initial condition between the wind and pressure fields, and that leads to the history of development of numerical weather prediction. So the name of the game here is that we want to find a balanced adjoint initial condition, which we put at the final time, between the winds and temperature sensitivity. So one thing came into my mind is the potential vorticity and its characteristic of invertibility. So we all know PV, most of us. It's a combination of relative vorticity and static stability. And it is conservative for inviscid and adiabatic flows. Ertl PV is conserved along isentrope on the left. Quasi-geostrophic PV is conserved on isobaric surface on the right. And we want to use this invertibility, which states given a distribution of PV within the domain at a balance constraint, one can recover the winds here and temperature fields associated with it. So to derive the sensitivity to PV, we follow the Abelgas 1998. Here's the general form. We want a definition for PV, a definition for a balance constraint, and we find these operators operating on size and on phase. With this is strain function, this is geopotential, and we adjoint that. So the star is saying we take the adjoint of the operator, and that gives us the sensitivity to PV, Q, and to imbalance A. And I want to give an example of the QG form of it. So we define QGPV here as this, and we use the geostrophic balance condition. So psi prime was 1 over F phi prime. And we find these operators R's. So our phi, our psi would be del squared, Our phi will be ddp f over s ddp, operating here on the phi, and t will be 1 just here, and t phi will be minus 1 over f. We plug those in into this expression, and that would give us the sensitivity to QGPV and to geostrophic imbalance. And note this operator is the exact same operator for QGPV when for calculating QGPV, and the inverse of it is the same process as we inverting the QGPV using the successive over-relaxation method. And that is what we want to get. There's also invertibility to sensitivity QGPV if we take the adjoint of the expression for QGPV. So dVGdx minus dUGdy, and there's a theta term. We adjoint this. So this term, take the adjoint, it would be ddy of q hat, and take the adjoint of this term, it will be minus ddx of q hat. And same as with the temperatures, or geostrophic balance temperature sensitivity. So what it says that if we have a positive sensitive QGPV, we would have a cyclonic sensitivity to winds around it, and warm sensitivity above and cold sensitivity below. And that is the same with when we have a PV perturbation, we have cyclonic winds around it, warm above and cold below. And if you're really not familiar with sensitivity, you can just think of it as a perturbation. And going through this flowchart, we have a unbalanced or full sensitivity to winds, to temperature, we derive sensitivity to strain function, to geopotential, and then to the sensitivity Q, to PV, and at the finally we'll have sensitivity to balance winds and temperature. And so the perk of using sensitivity to PV is that it combines sensitivity to winds and to temperature instead of interpreting them individually in the previous study. It also provides the geostrophically balanced adjoint fields here that we can plug in to filter out the gravity wave that we saw. And here's the result. We have the model going forward. We specify the response function at final time and let it go backwards. And this is the original output that requested. On the left, if we take the U and V and theta hat at this time and generate the geostrophically balanced sensitivity to winds to temperature at F23 and plug it backwards and let it go backwards in time, it gives us what we see on the right. So you can see on the left there's a gravity wave pattern on the western coldness, and you don't see that with the filter version. And surprisingly, with the filter version, you keep these features quite well. So cyclonic features around cyclone and along the cold fronts pretty well, and you can also see that in the unfiltered version. So I just want to refresh you of what this case looks like in terms of PV in the low level and in the upper level. You see a conservation of PV in general, but the creation of PV at lower level and erosion of it at upper level due to diabatic heating. And we're now taking the adjoint of sensitivity to PV in black contours, here at 500 and here is 300. And back on the left is QGPV, on the right is Ertel PV. So here we see that we want more sensitivity to PV where it already has a high PV for the storm to intensify that final time step. And looking at just one time at F12, you see here we have a positive sensitivity positive QGPV in the forward run, and a positive sensitivity to it, kind of north to it, and we have a cyclonic winds, a geostrophically balanced cyclonic winds around it. Same as with 300, when you see a positive Ertel PV in the background, and we have a more sensitive, we want more sensitivity, we want more PV here for the storm to deepen, and then we want less PV here for the storm to deepen. And looking at 850, here is the sensitivity to temperature or geostrophic balance temperature, shaded, and QG sensitivity QGPV again in contour. And we want to take a cross section around the front, and give us what we see on the right. So this orange feature here is all positive sensitivity QGPV, and above it, or above the maximum of it, is this positive sensitivity to warm temperature, sensitivity to cold temperature, and here the background is just the theta, background theta. And see, behind the front you have a northerly flow, or sensitivity to northern flow, and in front of front you have a sensitivity to southerly flow. So it's again cyclonic around the positive sensitivity PV, and it's just follow the front tilted negatively. So a conclusion for this part is that we use balance sensitivity as adjoint forcing, and it allows us to filter out the sphere's gravity wave in the adjoint model. Then sensitivity to QGPV combines sensitivity to wind and to potential temperature. And again, positive PV, cyclonic wind, warm above, cold below. And the third part, I want to talk about sensitivity to imbalance. It's a new idea. It's a byproduct of deriving sensitivity to QGPV, and Albogas discussed it in his work only about the PV, but he ignored the imbalance part. So I want to understand what that is. It's kind of a scientific question in my dissertation. So I want to give you some refresh on what is geostrophic imbalance. Just geostrophic balance. We have the geostrophic waves defined as -1/f dt dy and -1/f dt dx. We take the y derivative and x derivative of it and derive the vorticity, geostrophic vorticity as 1/f del squared phi, and we can write the vorticity in terms of strain function, and we cancel out the del squared. But is this true? Here I give you the JRA reanalysis at 500. On the left is strain function, on the right is geopotential. You can see, because we always have positive vorticity, usually have positive vorticity in the northern hemisphere, so the strain function field is overly negative. And we know it's always true for the geopotential to be positive in either side of the hemisphere. So it's apparent that we cannot have a negative feature equal to some positive feature. So it's not the full strain function that is equal to the geopotential, but it's the strain function that is equal to the perturbation of the geopotential, 1/f of it. And now we plot the background geopotential shaded here, and strain function in black, P'/f in red. So we see they matches pretty well in the case of our November windstorm. And now we can look at what is meant to have a imbalance, or the definition of geostrophic imbalance as the deviation of the strain function, the actual strain function from the geostrophic balance one. So again, if we take the derivative of our imbalance, it kind of says that the unbalanced component of winds derived from A is similar to geostrophic wind, except we don't have the divergent part. So in this figure, I plotted geostrophic winds in red and unbalanced winds in black. You can see it's mostly, they agree on each other pretty well in terms of magnitude and direction over the region of trough. It's both, they are both easterly, saying that is subgeostrophic over the trough region. And if, so this says that a wind associated with imbalance perturbation is close to geostrophic winds, but it doesn't have the divergent part. If we take a look at the linearized shallow water equation and take the derivative of the momentum equation, that gives us the divergent equation. We can rewrite this in terms of geopotential and takes out the del squared. That gives us time tendency of the velocity potential is equal to F times the imbalance. So that says the wind associated with imbalance is geostrophic without the divergent part, but the imbalance itself is related to the time tendency of divergence. So remember that's our expression for sensitivity imbalance, and here's the QGPV operator. If we ignore the geopotential part and only focus on the strain function part, we notice because they are all taking a second order derivative, when we have a configuration of positive A above and negative A hat below, you would have a positive strain function sensitivity above and negative strain function sensitivity below. And with that, you will have a anti-cyclonic winds or sensitivity above, cyclonic sensitivity below, and given time and Coriolis force, it will torque the winds to the right in northern hemisphere. That gives us sensitivity to divergence above, convergence above, divergence below, and due to the continuity equation, we would then, given time, having a downward sensitivity to downward vertical motion between a positive A hat above and negative A hat below. If we only look at the geopotential part and notice this time the A has the opposite sign of geopotential sensitivity. So when we have a positive A hat above and negative A below, we would have a dip in the sensitivity to geopotential above and the caving of sensitivity to geopotential below. And in between, we have a thinner thickness, which is indicative of we want to have a lower temperature in between. And given the geostrophic adjustment, we might want to bring in adiabatic heating by downward vertical motion. So these two figures kind of agree on each other by saying when we have a positive imbalance above and negative imbalance below, we would all want a downward vertical motion. Any questions? Yes.
I have a question. It might have been from a little bit earlier though. So you were showing the plots where with the kind of ugly plot with just the wave and how it rebounded from the sides. Maybe I missed it, but in your sensitivity analysis, how do you ensure you're not just seeing some boundary effects happening in your model?
I plug in the balanced adjoint sensitivity, so that would allow it to filter out the gravity wave by general.
Okay,
Yeah.
thank you.
And here's showing the schematic figures, and we can also derive the actual unbalanced winds or sensitivity to unbalanced winds from knowing the sensitivity to strain function and sensitivity to geopotential. That is correlated with, that is known if we know the sensitivity to imbalance. And I'll leave the derivation here. So looking at 500 hectopascal sensitivity to imbalance in shading, and we want to take a cross-section of it along the jet. and I should know this F14. So if we want to intensify the storm 10 hours later, the imbalance shows that we want to have more warm temperature here at this region, more than to the jet, and cold temperature kind of beneath the jet. So we have the configuration of positive imbalance above, or sensitivity imbalance above, and negative sensitivity imbalance below. And in between it's a cold temperature sensitivity. And to the north of it, we have a negative sensitivity imbalance above and positive sensitivity imbalance below, and that gives us a sensitivity to warm temperature at this region. We can also see if we plot the sensitivity QGPV at this region, and we notice kind of showing that it wants to intensify the PV in some sorts, but it kind of leaves out these things unexplained by QG balance. So now we want to compare sensitivity QGPV and the geostrophic imbalance in terms of the winds and temperature inverted from them. So the shading here on the left is showing the full wind sensitivity from the warp output. That contour shows the geostrophically balanced wind. The gray contour shows the unbalanced wind component, and you can see the geostrophic balance component explains most of the wind sensitivity. But looking at the temperature sensitivity, again the full ones is in shading, unbalanced one is in the green contour, balanced one in black contour, and you can see the temperature sensitivity is mostly explained by the unbalanced component, or the one that inverted from geostrophic imbalance. And now looking at the cross-section around the surface front, and in the background I plotted the accumulated precipitation until F14 for this event. In this cross-section we see a uniformly negative sensitivity to imbalance above and positive one below, and in between is a sensitivity to warm temperature. But we want, so this is just front, and you can see that. And we wonder why they are showing at these two locations. Normally one of front to intensify, maybe just a lower level, but why we're seeing that at like 500 and maybe 400 hectopascal. So here I plotted the convective ring precipitation in orange. Here you can see where we have more convective precipitation, it kind of co-locates with the location where you have more warm temperature sensitivity at lower level. But looking at here, when I've plotted the stratiform precipitation, it's kind of happening at the same level as this warm sensitivity region. So it is kind of indicative of saying that the unbalanced temperature sensitivity is somewhat associated with diabatic heating. And finally, we show the optimal perturbation that is proportional to the sensitivity, the full sensitivity. And now we just want to show what happens if we only put in the balanced sensitivity and the purely unbalanced sensitivity, or the perturbation, sorry. So if we remember our motivation for creating a balanced sensitivity field is we wanted to filter out the gravity wave. And you would naturally think maybe the unbalanced part is entirely the gravity wave. And we know the gravity wave, they don't stick. They dissipate and expand out of the boundary. So only look at the balanced part. We put in balanced perturbation here to the winds, in contour, to temperature, temperature perturbation in shading, and that leaves us to 24 hours later, when we subtract the control run from the perturbation, a deepening storm. But surprisingly, if we put in a purely unbalanced perturbation informed by the unbalanced sensitivity, in this figure, and same contours of wings and shading is the temperature, it also deepens the storm by about the same amount. So we can see back and forth how different these initial perturbations are, right, between the balanced one and unbalanced one. And they lead to pretty much the same change in final time sea level pressure. So this kind of saying that we cannot ignore the unbalanced components, even though there are a lot of gravity wave features in it. So the conclusion I want to give for this final part is that the sensitivity to geostrophic imbalance, it also combines sensitivity to winds and to potential temperature together. When we have a positive sensitivity to imbalance above and negative one below, like here, it suggests that we want a cold temperature sensitivity in between. And when it's negative above and positive below, it gives a warm temperature sensitivity, and it's unbalanced. And we also further find that QG balanced wind sensitivity explain the majority of the full wind sensitivity, and unbalanced temperature sensitivity explain the majority of the temperature sensitivity. And we find that unbalanced temperature sensitivity is related to precipitation and maybe to diabatic heating, and that gives you this extra amount of temperature sensitivity. And both purely balanced and purely unbalanced adjoint sensitivity informed optimal perturbation can lead to change in decent amount of change in response function. So for the future work, I want to better understand what is imbalance, and then adjoint sensitivity PV is in development. And finally, after graduation, maybe address the unbalanced component in the background error covariance in data assimilation. And so that's all I have today, and thank you very much. Questions? Ian.
I have a question, Bill. If you were to go back like 3 slides where you were flipping between the unbalanced and the balanced initial condition perturbation, so it strikes me that the balanced initial condition perturbation is a much smaller magnitude than the unbalanced ones.
Yeah, it is, in terms of the temperature perturbation.
Okay.
But the wind perturbation is much stronger than
I see.
the unbalanced one, and that is kind of what we see in the sensitivity field.
Interesting.
Right, because the perturbation is proportional to the sensitivity.
All right, I see.
Yeah.
So yeah, I had a follow-up question, but I wonder if that kind of clarifies it. I was going to ask, in terms of an application, it seems like you need to run both tests. If you want to make an ensemble, you need to run some with balanced perturbations and then some with unbalanced perturbations, and then you can get a spread by varying the response function. Is that kind of an application of this?
I think, well, you can ask Kari more on that. She runs the singular vector, and that kind of take the eigenmodes, like the first and second eigenmodes of the adjoint informed perturbation, and that kind of gives you the most variant ensemble runs that you can get from different perturbations. So the balanced and unbalanced one is just saying that we cannot. It's kind of counterintuitive if we think the unbalanced is only the gravity wave part that we filtered out. And it's just, I'm showing this because it's surprising to me that it can also lead to decent change in the final time perturbation. But normally people putting optimal perturbation just proportional to the full sensitivity, not saying the balanced one and the unbalanced one.
Got it.
Yeah.
Thanks.
Mm-hmm. Yes.
So I'm still trying to understand that how you are perturbing this system. So you said that it's a time-varying thing, but do you also spatially decide where to introduce the perturbation, or it's not a spatially dependent thing? Like, do you?
We only introduce the perturbation at the initial time step, so it's not temporal, and spatially it is proportional to your sensitivity and its location at different space or different, well, this is spatial location, right, of the sensitivity.
So the entire domain is not perturbed, but just a specific location based on the sensitivity is perturbed?
Yeah, where you have zero sensitivity, of course you wouldn't perturb it. Because if you're putting a very huge perturbation where you don't have any sensitivity, it wouldn't lead to any change in the response function.
Okay.
Right. Gerald didn't need.
Yeah, so in general, what can we learn from adjoint sensitivity tests? Like, do they tell us how to improve forecast models, or what is this for specific events that you're trying to model better? Or
I mostly use that for case study, the adjoint sensitivity. In general, we don't need to run an ensemble run to determine where somewhere is very sensitive, right? You can compare different runs, you can perturb the initial condition in winds and run one model, one simulation in temperature, in another simulation, and that you have like 3 or 4 different runs, but in the adjoint model you only integrate it backwards one time, and it gives you the sensitivity to all the variables. Right, and the sensitivity is mostly used, the adjoint is mostly used in data simulation, where you have in 40 bar, where you want to take the observation back to your analysis time step.
I think I asked you this before, but for the rainfall, you do cross-section through the front.
Mm-hmm. Which one is the?
When you show convective versus stratiform rainfall.
Right.
So does the aggregate of both convective and non-convective play a role, or are you just basing off of, in terms of temperature sensitivity? I can tell that there is a sensitivity to convective rainfall there, and then non-convective on the left-hand side. But does the combination of the two play a role?
I think so. Yeah, if you're just looking at where the diabatic heating is introduced, I think both convective and stratiform precipitation gives you different amount of diabatic heating, and this is kind of indicated by the temperature sensitivity. So I think it adds up linearly because the adjoint model is a linear model.
And is this what my physics school are using?
It doesn't have one. The adjoint doesn't have, but the forward run has one. And that's why we don't have other sensitivity to other moisture variables such as hails and ice and rain.
That's what I was going to ask that.
Yeah. Sorry? Do you want to come to this?
Yeah, there isn't any further question. I think maybe we should tell the speaker. And yeah, so thank you.